Hello, sir. We are live now. You can start.
Okay, thank you.
Okay.
I have a class later. Okay. All right. So, good morning, everyone. Okay. All right. So, good morning, everyone. As planned, we will be continuing our discussion on deep learning. And so, today we are going to begin a new series. Last week, we had, I don't want to call it an introduction, but we had a semi-introduction of neural networks. I mean, the practical session, and then we looked at why you would need non-linearity in the system. So we motivated the idea behind, you know, the inclusion of the non-linear activations and how it can help improve the system. So today we are going to continue in that line, but we're going to do more practical applications. Okay, so we're going to be talking about computer vision. All right. So by the way, this note is from Mr. Mr. D Book from GitHub. You can always look it up for more resources. It has great resources there. Okay, so we'll be talking about computer vision today. What does that really mean? I'm sure some of you must have heard the word computer vision or vision for a short. What does it mean? Okay, it just means that we're trying to make computers, to teach computers how to see. Okay, just like human vision. As humans, when we see things, we recognize them. The brain helps us recognize the items that we see. So we're trying to replicate this kind of ability in computers. So it's a whole field, okay, and that in computer science, and that field is actually called computer vision. So we're going to be using deep learning techniques to try to achieve this goal. I'm sure you would also have heard in the previous class we talked about different types of classification. For example, we talked about binary classification, where we're trying to classify whether an object belongs to one class or the other. So there are two classes in this case for binary classification. For multiple classification involves more than two classes. So maybe given an image, you want to identify whether that image is an image of a cat or a dog or a chicken. That's three classes. So the moment the number of classes exceeds two, then we think of multiple classification problem. Okay. There are other vision tasks. For example, we can also do object detection. So this is an example of an image, and we want our model to be able to put a bounding box around the object that we care about. It's like saying, where in this image is that object? So this is the image of a car, and then we want our model to be able to, tell us where in the image that car is by putting a bounding box around this. So this particular problem is called object detection. It could be classification, where like you give the model an image and you want the model to tell you whether the image belongs to one class or the other. In this case, this is image of some dish. You want to be able to tell whether the image is that the image of some This is fried eggs, I guess omelette or something, and meat or pizza. Okay. All right. So if it's more than two categories, then it's called a multi-classification problem. Okay. You can also have another type of vision task which involves segmentation. This means you want to categorize the pixels within the image. So you want to categorize some pixels as background and some pixels as foreground. Okay. So given this image that you see on the far right, you want the model to be able to isolate every other thing, okay, and only produce delineates the image that you or the region that you care about. So this is a segmentation problem. So in the hood, it's actually a classification problem because you're doing pixel classification in this case, where you want a pixel to either be a foreground or a background. All right, so that's about the different types of vision tasks. So what we're going to cover is how to train these kind of models. Okay, so this is the workflow, typical machine learning workflow. You get the data sets, you turn them into tensors, okay? And then you can search through the repository of models that have already been trained, or you can build yours yourself, okay? And then you fit the model, you evaluate it with some evaluation metrics, and you can improve it through different experimentation. And then you save and reload the model for use. All right, so in this topic, in this notebook, we're going to be looking at these various topics. For example, loading the data, how do you load the data, how do you prepare the data, how do you build your own baseline model, how do you make predictions and evaluation, how do you set up agnostic code for future models, and remember last week we talked about non-linearity, how do you add non-linearity, and very importantly, what are convolutional neural networks and how do they improve the model. All right, so that's what we are going to look at today. So we'll start by executing the first lines of code. So if you have the notes, you can follow through. So the first thing here is we import the touch library, okay? The sub module, the neural network module under the touch, and these are all packages that we'll need to work to train or to build this model. Okay. So in this very tutorial, we are going to be using a particular data set called the FashionMNIST. Okay. So the MNIST here stands for Modified National Institute of Standards and Technology. Fashion in this case indicates that the images are all fashion images. So these are images collected, very low resolution images that have been collected over time of different clothing items. Okay. And the model we want to build here is one that identifies which clothing item a particular input belongs to. So it's a classification problem. So for these data sets, there are 10 categories of clothing items. Okay, so you see these categories. It was made possible by Zalanda Research, and this data set is similar to the standard MNIST data set, which contains different categories of houses, cars, and the likes. Okay, so we're using the FashionMNIST. You can follow this link, okay, to get more details about the data set. So that's that. So because there are 10 categories, this is a multi-classification problem, and we want to build a model to be able to do this identification. Okay, so to load the data set is actually very simple. PyTorch provides us with a simple way of loading these standard data sets. Okay, so this code here loads the data sets. In fact, it doesn't just load it, it converts it to tensors for us. Okay? So we want to load the training data set. We want to download it if we don't already have it locally. And then we also want to convert it to tensor. Okay? There are no target transforms for now. So this is the training data. Okay? Why? Because we set train to true, so it downloads only the training data. And the next part is the test data. So we set train to false. In this case, what we will get as a test in this variable will be the test data set. So if you don't have it locally, then this code will download both the training and the test data sets. Okay. So like I said, this data has already been converted to tensor. We can take a look. So here we only just looked at the first example in the training data, and then we show the image and the label. So in this case, this large tensors of zeros, okay, is the image. It's a lot, okay? And the last part is actually the label. So label number 9 stands for something. We're going to look at it in a moment. So like I said, we have 10 labels, okay? Each label an integer value, okay? So for example, a shoe can be assigned to maybe 5 or any other number between 0 and 9, okay? Now, these images are low resolution, okay? This is so as we can be able to train it on our local system. But in real life, the images that you're going to use are going to be of much higher dimension than the one you see here. So it means that you're going to need a much larger, bigger, faster computer to be able to train these models. So just for a start, we can look at the shape, okay? Now the shape of this image is 1 by 28 by 28, okay? The first, obviously this is a one, the number of dimensions of this tensor is 1, okay? But it has, in that dimension, there are 3 variables, okay? So this is actually a vector of 3 items, okay? Now the first item indicates the channel. So because this is a black and white image, you only have one channel, okay? And the next 2 part indicates the dimension of the image. So this is a 28 by 28 pixel image. Okay, so this basically just shows the idea. So we have the image of some image of a clothing item. It is 28 by 28 because it's black and white. This is what you see. Okay, so 28 by 28 image. So the shape is 28 by 28. It's 3 dimensions. Sorry. Okay, so we have the image, and this image is going to form the input to our machine learning model. And we want to be able to predict some outputs that has values between 0 and 10. So by the way, if you have any question, okay, if you have any questions, probably type it in the Telegram link, or send it to the Google channel. I can see your comments and I'll be able to answer. Okay, so let me do a recap. So this is a 3-dimensional image. Okay, the first dimension has value 1, has 1 variable. The second dimension has 28, and the third dimension but the 0 dimension has value 1 value. The 1st dimension has 28 items, and the second dimension has 28 items. So it's a 3D image. Okay, like I said, the 0th dimension indicates the channel, okay, and the rest indicates the height and the width. Okay, we can look at all the training data. and their shape. So to do that, if you do train, since this is a dataset object, okay, it comes with a dataset attribute within that data attribute within that dataset object. So if you do length.data, it should tell you the total number of the data points in that attribute. And so we are looking at the number of training data, okay, the number of the targets. The target indicates the Y value, okay, or the class that they belong to. So we do that for both the test and the training data. So here, as you can see, there are 60,000 training image, okay, with their corresponding 60,000 labels, okay, and there are 10,000 that will be reserved for testing the model with the corresponding 10,000 labels. Okay, we might also be interested in looking at the classes. Okay, so there are 10 classes, like I said. An image can be a t-shirt or a top. Okay, all right, can be a trouser, can be pullover, can be dress, can be coat, can be sandal, can be shirt, can be sneaker, can be bag, can be ankle boots. Okay, so this indicates the classes that each of the images belong to. And because there are more than two, this is a multi-classification problem. Okay, so here we take a look at an example of such image. Now, if you look closely, you see that this looks like more like a boot. Okay, so what we do is we first of all we take a sample of the image, the first image in the training set. We print its shape. Okay, of course, you see there's a 3D tensor, 1 by 28 by 28. Okay, and then we just do an im show to visualize the image. And lastly, we print the label. Okay, so the label for this, okay, is 9. So it means that our model should be able to produce 9 whenever it sees this kind of image. And 9 represents the boot. Okay. So what is the best model to train the data that has images without labels? So that is an unsupervised problem, and there's something called Occam's razor. There's no best model for anything. Okay, there are lots of assumptions that you have to put into any model that you have for you to be able to get a good result. So there's no ideal best model. Okay, so most of these things happen based on prior assumptions about certain conditions, and then you can bake all that into any model that you choose to give you the right result. But we do know that certain types of models or classes of models have been shown to work very well for certain classes of problems. For example, as you'll see later in the notes, convolutional networks tend to work very well with images. And if you want some sort of recurrence, some sort of time series prediction baked into it, you might want to look at more into periodic models, maybe Gaussian processes, recurrent neural networks, and there's a zoo of techniques that you can apply. So there's no quote unquote best model for anything. All right, so okay, I don't know if it's clear now. It's zoomed. All right, so this is so for this input, this is a boot, okay, and its assigned label is 9, so it means that every boot should have value 9. If it's not 9, then it means that the model is not predicting what we want. Okay. All right, so okay, so this is actually an ankle boot. Okay, so here we just do an im show. Okay, we squeeze it. So this squeeze, what it means is we are taking out the excess dimension. Okay, the shape of this thing is 1 by 28 by 28, but the im show only takes in a 2-dimension tensor or NumPy array. So we had to squeeze this up. So to squeeze this up, we'll turn this into 28 by 28 instead of 1 by 28 by 28. So this is why we have the squeeze method inside. Okay. And we can also decide to show this image in grayscale. So we can change the CMAP to grayscale and then get the actual label for the input. In this case, it's an ankle boot. All right. Okay. So let's also explore other images. So here we created a grid, a 4x4 grid. So we're going to show about 16 images, okay, in each grid, in each cell. So we do a loop, okay, and then for each at each time we randomly, sample within the training data for an item, and then we show it. So this is what this does. We take a random sample, okay, that goes between 0 and the length of the data. So it's going to pick a random index from the data, okay. We use that to sample the training data, and then we show it at each iteration. So when you do this, you get some 16 by 16 grid, okay, 4 by 4, which is 16 images. So this gives us like a clear picture of the type of data set that we have. Because this is the ankle boot, there's the shirts, this is sandal, okay. This is coat, this is a pullover, sneaker, and the likes. All right, cool. So we've been able to explore the data set, okay. So this is what we want to work with, all right. The next thing is to prepare it in a way that we can pass it to a PyTorch model, okay. And to do that, we use something called a DataLoader. Now, this is very, very important because the DataLoader, as the name implies, helps you load the data from a particular location, okay, into memory so that your PyTorch model can use it for training, okay. This is also very important for those of us who would have a system with limited memory capacity and also limited. Okay, my laptop is not charging. Okay. For some of us who have limited memory capacity system, this will be very helpful because we can properly manage our memory. Okay. All right. So we have the data sets. We use the DataLoader to load it. Okay. And the idea is we can now specify the batch, okay, the batch size for each iteration. So what does that mean? It means that as the model is running, it will load certain images at a time, okay? We can specify a batch size of maybe 32 or 8. If you specify 32, it means it will load 32 images at a time, okay? If you specify 8, it means it will load 8 images at a time. Now, with that, you can now set the batch size based on the capacity of your computer. If you have a computer with very low RAM or low GPU memory, then you might want to load smaller batches. If you have a computer with high capacity, then you can increase the number of batches. That's just what it's used for. Okay, so here we specify a batch of 32. And then we specify a train loader. It takes in the data sets, which is train data here. We specify the batch, and we want you to shuffle the training example each time we load. Okay, we do the same thing for the tests, and then we can just print out a few stuff here too. Okay, so here we have the length of the data train loader is 1,875 of 32 batches. So if you do the multiplication, you will recover the actual training data, number of training sites. And then you have also 313 of 32 batches. All right. So to work with these batches, they are actually iterators. Okay. So to work with them, you can just simply do a next. Okay. All right. And you see how it retrieves the data from the training loader. So what you see here is I do a next on the training data. I wrap it around the ITA function, and I do a next of that, which will retrieve a batch at a time. So once you do that, we can print that batch. We can print the shape of that batch. So this is what you see. Okay, there are 32 images here retrieved because there are 32 batches, and each image is of size 1 by 28 by 28. Remember, the one here indicates the channel, and this is the height, and this is the width of the image. The corresponding label just has 32 values. So you give me a few minutes. Let me try to see if I can charge my computer. I'll connect again. Just give me a few breaks. Right. So sorry for that. Sorry for that breaking transmission. Okay. Okay. So okay. Hello. Hello.
Hello, sir. We can hear you. You can continue.
All right. So I don't know if okay. All right. So yeah. So like I said, the batch. Okay. So we specify a batch size of 32. We wrap the data loader around the trained data. We also wrap the data loader around the test data for both train and test. Now um, we can just just print out um, we can just print out the train and test loader. As you can see, they are all instances of object of data loader. We can check the length of training, and we can also check the length. All right, and so that's that. And like I said, we can wrap an iterate around the train loader and just go to next. So in next, um, uh, we retrieve the data from the train loader, and to do that in an iterative way, just like doing loop. Okay, so by calling this method, I, I get a batch from my training data sets. All right, so here we batch, the shape of the train features and the shape of the layout. So we specify a batch of 32. Okay, 32 images here, each having 1 by 20 by 28. Of course, there are corresponding 32 labels for those images. Okay, all right. So that's that. Okay. Now we can see that the data remains unchanged even by checking a single sample. So now that we wrapped it around uh, the train data loader, we can just do a sanity check to see that the data is still intact. Okay. All right. So let's see if if there are any questions, just type it in the chat. Now. Okay. All right. So it's time to build a base model. So what really is a base model? A base model is what you actually build yourself. Okay. It's not so big deal about it. So so to build a base model, just like you saw in the previous class, we just create a class that extends the module. That's all. Okay.
So our base made model will contain two linear layers, okay? And each linear layer is represented by this neural network of linear. Before we pass to a linear layer, we will have to flatten it up. Okay. And if you look at this image, it is actually 1 by 28 by 28. So we need a single vector. Okay. To do that, we'll have to flatten the image. Okay. So what does flattening does? It just simply turns multi-dimensional to a single vector. So all module has. Okay. So this is just to do a test to see what they work. So I make flatten layer. Okay. It is not a learnable layer. It just flattens it. So we shift it. Okay. So now we pick some sample, the first sample from our batch, and then we pass it through a flattened layer, and then we just look at the shape. Okay. All right. So this X is before we pass it through the flattened layer, and the output after we pass it through the flattened layer. So you would see that before passing it through the flattened layer, you have the original dimension input, which is 1 by 28. And then after flattening it, you have a vector. Okay. And that's what we try to. So as you can see, before flattening it, you have 1 by 28 by 28. But now after flattening it, you now have 1 by 784. Okay, which is 28 times 28. Okay, that gives you 7. This is still one image, but it's now a vector. Okay, now in this case, this part now represents the batch. Okay, so that's that. So with this, we can build this version of our neural network, which is this guy here. Now notice it's just a sequential layer. Okay, the first thing it does, it flattens every object that comes in. Okay, and it passes it through the first linear layer, which is matrix multiplication. Okay, and that dimension is going to be hidden input by input shape. Okay, then the result of that is another linear layer. There is no non-linearity here. Everything here is linear. So that's that. Okay. And we can initialize the model. All right. Pass it and send it to CPU or GPU, what you have. Okay. All right. So please a bit more. Okay. So we are making a simple neural network. The input shape 784. We intend to flatten every image. Okay, so that gives 784. We have 10. It's a one layer neural network. So the hidden layer has 10 neurons. Okay, and then the output layer would have the total number of classes. Okay, so if you print this, you would see that the first thing comes flat layer, passing through the first transformation, which is 10 by 784 by a 10 by 10. Okay, we can set up the loss function. So here we just some import some function from the internet. Okay, and then we set up the loss function. Now we are using the cross entropy loss. Remember, the cross entropy loss, okay, is for a multi-classification. Okay, and then we use the the plastic gradient optimizer. If you recall from our previous class, I said the loss, okay, is a way of measuring how well your model is doing versus the actual prediction. And then the optimizer, okay, helps you tune those weights. And what are those weights? The weights are these matrices. Okay. So that's what we set up here. And then we these are just methods. So call the training time. Okay, and then we do the training. Okay, it will take for a while. So this is the training. Okay, so this is at 0 sample. This is the first sample, 12,000 sample, and so on and so forth. Okay, so we're training it for 1 epoch, 3 epochs, sorry. Okay, so after the first epoch, we get a training loss of 0.59 and the test loss of 0.59. The accuracy is 82%. Okay, after the second epoch, we get an accuracy of 80%, test accuracy. After the third epoch, we get an accuracy of 80%. So it looks good. I mean, it does well. Okay, it's not so bad. All right. But let's look at the predictions. Okay. So for this, we have this evaluation function, which takes the model and the data loader, the loss function, accuracy function. So with that, you can study this itself. With that, you can simply now do an evaluation. Okay. The name of the model, we call it FashionMNIST1, model 0. And we got a loss of about 0.5 and an accuracy of 83%. So it means 83% of the time the model gets it correct. Okay. Now we train this model on the CPU. Okay. If you have a GPU, okay, you can use the GPU. Okay. Now to do that, you're basically going to just ask if you have a GPU device. If you have a GPU device, then you set the device to CUDA. Otherwise, on this machine, I don't have a GPU. So what I'm still going to get is a CPU. Now, from the previous notes, we talked a lot about non-linearity. Okay, and how powerful. So the model you just saw here, okay, all right, is a linear model. That's most model we define. Okay, there's no non-linearity. Okay, it does okay, but we can do better with non-linearity. All right, so which is what we are talking about here. Okay, so we can build in a better model with non-linearity. So what do we do? Well, after every transformation, we pass through a non-linear function called the red. Okay. All right. So after the next one, we pass through non-linear division. Now let's see how this would do based compared to the previous one. So the previous one was about 83%. Let's see if we get a better. Okay. So instead of the same model, it's now version 1, the same loss. Okay. And with the same training, 3 epochs, and let's see how we do. So this is model version 1, okay, or with non-linearity. Okay. Okay. Now, you will notice that the model is training a lot. In fact, we didn't even do very well. So this is after 2 epochs, we have 75% compared to 83%. Okay, and it's even training slower. So the question is, are you to use a GPU? Well, in this case, there's no GPU anyway. So now the question is, why are we now getting um, uh, lower performance? Okay, even when we do non-linear. So my guess is that there's probably a lot of overfitting happening. This is why we are um, was okay. That's evaluate. Okay. All right. So we got the performance. Okay. Um, okay. I think if you run this, you're supposed to get an error. Okay. This is because I'm still on GPU. So I'm supposed to get an error here, which shows that some models are actually supposed to be moved to the same GPU for you to fix this problem. Okay. So if you're running this on Google Colab, then perhaps you might see this error. Maybe by fixing it, you'll get a better understanding. Okay, so start. So our first version gets 5%, and second version, uh, first version, second version gets 5. First version actually does better. Mm. In this case, it looks like having performing worse than the baseline. So that's the thing about the measurement. Sometimes you thought it should work, but it doesn't. And then the thing you thought might work does not. So it's part of the science. Okay? So like I said, non-linearity may tend to overfit your model. And what is overfit? Overfitting simply just means that you're doing so good at the training set for doing that. So from the looks, it seems that our model is now overfitting on the training data. Overfitting means that our model is learning the training data well, but those patterns aren't generalized to the test. Okay? So the two main ways to fix overfitting. Use smaller and different model. Okay. The models fit certain kinds of data better than others. Or you can use a larger data set. More data and the model chances meet as to learn the generalized pattern. Okay. There are more ways to fix this, all right? But it's something that you uh, at your own time. Okay. So now come we have model learned too much. Okay. So that might be the reason why it is now performing less than it should. All right. So now comes convolutional UML testing. Okay. All right. So they are great at working with images. Okay. So let's look at what Wikipedia defines. Okay. So a convolutional neural network is a polarized type of feed-forward neural network. So what you saw in the previous example, feed-forward neural network. But for a convolutional network, it is polarized by a filter. Okay. So the sound is not clear. Okay. Okay. I think that's because I have this running at the same time. This All right, so okay. I don't know if yeah, I think I'm back now. Okay, so all right, so I guess we continue. Okay, so let's do a recap. Okay, so we're talking about convolutional neural network. Okay, um, so I said that the convolutional neural network is a regularized type of feed-forward network. Okay, now the cool part with this convolutional neural network, okay, is that it learns features, and you'll see that in a moment. Okay, now it learns these features by the use of something called a filter. Okay, and these filters are optimized during the learning phase. Okay, but they have certain issues like vanishing gradients. Okay, and exploding gradients. All right, and these are the core problems that you might see during um, these training these neural network. But well, these can also be alleviated using the non-linear activations like ReLU and the likes. Okay, but so let's just continue. So yes, so a convolutional neural networks, they are actually known for their capabilities to find patterns. Okay, and since we are dealing with visual data, let's see if the CNN can improve what we have here. So at the moment, our baseline model is 75% accuracy. So we want to see if by incorporating a CNN, okay, into our baseline model, we'll be able to do better. So this is how we're going to set it up. So we're going to have our input layer, which will be our image, okay, and then we'll pass it through a convolutional layer, okay. Then we pass it through an activation. Then we pass it through pooling, okay. What we get will be an output layer, okay. Now, where the content of the convolutional layer can be upscaled and repeated many times. So we can repeat this step many times, okay. The idea is we will now, by doing this, we can automatically extract different types of features from the model. Okay. So what model should I use? Wait, you can say CNNs are good for images, but are there other types of models that you should be aware of? Yes. If you are using structured data, maybe data from Excel that contains rows and data, then of course you can use gradient boosting method, random forest, those things that Ms. Khadija taught you in machine learning class. They will do very well. Okay. But if you are using unstructured data, maybe your data is you're working with these images, audio, and language, then convolutional neural networks and transformers are shown to work very, very well. Okay. If you want to learn more about transformer, you can follow this Hugging Face transformer link to learn more about it. So transformers are what power up your chat GPT that is now very famous. Okay, audio not loud enough. Let's see. Okay. Let's see if I can increase the audio. Yeah, my microphone is fairly large. Let's see. Okay. Just a moment. Let me see if I can try to increase my sound. Okay. All right. So my microphone is almost at the end, at the loudest now. So I guess I should be able to hear me clearly. Okay. All right. So. Okay. Okay. All right. Good. So, like I said, if you are dealing with structured data, then you can just use your standard machine learning models, XGBoost, random forest. They all work very well. But if you're dealing with unstructured data like images, audios, and language, okay, like text data, all right, then convolutional neural network and transformers have been shown to work very well. Okay. If you want to learn more about transformers, you can follow this link. Okay. So if you're with your phone, okay, you might want to see these CNNs in action. Remember, I said the CNNs are very popular because they automatically learn different patterns from the data. Okay, interesting patterns to be specific. So let's look at this CNN explainer website. Okay. So what you see here, okay, what you see here is some pre-trained model. Okay. So if you go back to the notes, you'd see that, yeah. So this is a pre-trained model. Okay. All right, that has been trained to identify different, types of food. Okay. And food, like different types of objects, essentially. Okay. So by clicking on any of these images here, you pass that image to the model. And these are the convolutional layer. So the first thing here is a convolutional layer, followed by a ReLU, and then another convolutional layer, followed by another ReLU, and then there's a max pool. I'll explain all this in detail. Okay. And then another convolutional layer, followed by a ReLU, another convolutional layer, followed by a ReLU, and followed by a max pool, and then you flatten it up and you get your predictions. Okay, so for example, I passed in this image input. This shows the different channels. This is the red channel, this is the green channel, and this is the blue channel. Okay, so clearly you see that for this very image, okay, the color, the heat map, or the color distribution shows the activation or what these layers have learned. Okay, if you look at the first convolutional layer, you will see that this is the red channel, so it has learned to learn most of the red inputs and the activation for that very input. That's that neuron, okay? But this other neuron is really blanking out, okay? This guy has learned something. Maybe is able to capture most of the green part, I guess, okay, and so on and so forth. Okay, so if you move down the layer, you will see that you see the patterns that this input has learned. And they actually trace out, the shape of the image, okay, until the final output. So for this input, the final output is a ladybird, okay. If you select this, you can see how information flows from several layers. So at the last layer, we flatten it up, okay, to a vector, okay, pass it through, add a bias, okay, and add a softmax, okay, which squashes it down, okay. And from the softmax value, you can see that the ladybug logic gives the highest, should I say, probability. It's not really, shouldn't be interpreted as probability per se, but okay, if you want to interpret it as probability, then you say when you condition it on this very weight, okay, the probability that this input is a ladybird is actually 0.984. Okay. Now the cool part is you can also, with this CNN Explorer, you can also give it your own inputs. Okay. So note this. You can also give it your own inputs. Maybe you select some image from maybe your folder. Let's see. I don't have any picture to use here. Let me just use this funny picture. Okay. So I just uploaded my own picture. Okay. And what is the prediction here? It is telling me that this is the prediction of a live boat, but this is actually not a live boat. okay? Because it's telling me that this is actually a live boat with high probability. But the picture I posted is actually the picture of a wave spectrum. I don't know if you can see my screen. Okay, it's just some picture of electromagnetic spectrum, something in physics. Okay, but the model here is telling me that that image is actually a live boat, which is highly wrong. Okay, if you investigate it further, let's even see the probability it gives it. It gives it a probability of 0.62, okay, which is not so confident. Okay, but so this tells you that, well, but this prediction is not so confident for the fact that it actually takes a probability of 0.62, which is not bad, yeah, to be fair. Anyway, so that's about the CNN Explorer. Okay, these convolution. So the point, the take home here is that this convolutional layer tries to figure out patterns from the image. Okay, so let me select image of a coffee. Okay, so you can see the layers have actually, they've learned, put more emphasis on the coffee image. Some neurons put more emphasis on the coffee image than others. Okay, and in the last prediction, if so, let's look at the class label. So this is the unit that works with coffee. Where is it now? Espresso. Yeah, this unit. If you trace out its activation, you will see that. Okay, you will see that this very unit has more, more value. Okay, its value is actually um, exponent of 864. Okay, which in total, if you divide it by all um, other score, you get a probability of 0.89, which tells you that this very input image is most likely um, um, espresso, which is a type of coffee. Okay, so that's your CNN Explorer. You can always check this out. You can also read more about what these CNNs do, the input layer, and maybe more about this explanation. I think I encourage you to play around with this. Okay, so once we have that, we can bake this idea into our CNN. Okay, all we just need to do is include the CNN layer. Okay, so here we specify the input channel, which is going to be input shape. Okay, and we also specify the output channel, output shape. Okay, the kernel size is the tiny little box, okay, that you use to convolve the image. So if you go back to the convolution itself, let's see with this if there's a visual explanation. Okay. Okay. So there's no visual explanation there. Okay. So the idea is that if you have a kernel of a particular size, then that kernel will multiply each input at each spatial location. Okay. It's like doing a dot product between the kernel and the input at each spatial location. And that corresponds to a single value in the output space. So I think the CNN Explorer explains this in detail. So let's take a look at let's see, okay. Let's take a look at this guy. All right, and let's look at, okay. So you can see that for each input, this tiny box is the kernel. Okay, you multiply that kernel with a particular location. Okay, to get a particular output. So let me play this again. Okay, so like in this case, this is this kernel going around each input, giving you the activation values at this kernel output. Okay, and this tiny kernel is what we are going to learn via back propagation. Okay, so we have two of this. All right, pass it through a ReLU, and we also have two of this, another ReLU, and then we follow it up with a max pool. Max pool basically means that for every kernel region, you take the maximum value there, and that gives you the max pool value. Okay, and the rest remains the same. You have your sequential layer, and then finally you flatten the whole thing. Okay, so this is the forward pass. You pass it through block 1, and what is block 1? Block 1 is this convolutional layer. Okay, then you pass it through block 2. What is block 2? Block 2 is this sequential layer. So the block 1 is the convolutional layer. It's also a sequential layer that is composed of two convolutional layers. Each convolution has a value. Okay, so that's that. We can see the behavior of a typical convolutional layer just by running a few samples. Now, if you look at this, let's assume we have an image. Okay, there are 32 images, and each image has 3 color channels and it's 64 by 64. Okay, all right. So we can take the first image. This is a random vector, by the way. We can take the first image, okay, show the shape, okay, and show the text shape, okay, and show the pixels that constitutes that image. And this is what you have. Okay. Yeah, so this is what I was waiting for. So this is what your convolutional layer does. Okay. All right. So you have an image. Okay. The input size is 5. Okay. You have one padding. So, and then you have a kernel size of 2 and 1 stripe. So if you look at the image itself, this is the image. There are 5 is a 5 by 5 pixel. But you have one padding. So it means you are padding this original image by extra 1 pixel. Okay, all around it. And then you have a kernel size of 3. So if you look closely, you see the red spots is a 3 by 3 kernel. And the stride is how much you move it to the right. Okay, so this is this is how a typical convolution works. Okay, we can see the output. All right, we can just test it to see how it looks like. Okay, so remember, this is our sample, just some random image. Okay, we can pass it. We can make a 2D convolution, specifying the number of channels, the number of output channels, and the number of the kernel size, the strides, and the padding. So this is a 0 padding convolution. Okay, it has 3 input channels, giving rise to 10 output channels. Okay, so which means that if I convolve over this my test image, I'm going to get instead of getting a 3 by dimensions by something dimension, I'm going to get as output 10 by the dimension, the new dimension of the image, which is based on the kernel size. Okay. All right. So this is it. Okay. So I have each image, and there are 10 output of this. If you count them, there are actually 10. Okay. Okay. So that's that. Okay. So this is the image, all right, before convolution, okay, and this is the image after convolution. Now I get an input of 3 channels, okay. After convolution, I get 10 channels, and this is because I specified that I want 10 output channels after convolving. Now the convolution is dependent on the kernel size and also the dimension of the convolution is dependent on the kernel size and the padding. Okay. All right. So that's that. Okay. You can also look at the weight of this kernel. Okay. All right. So because I have 10 output kernel, it means our 10 output shape. It means I'm going to have 10 kernels, okay, giving 10 kernels for that convolution too. So that is specified by, these um, these weights here. Okay, so there are 10 of this. Okay, for these two deconvolution, and each weight is actually 3 by 3. Okay, all right. So this is actually a 5 by 5. Sorry. So this is actually a 5 by 5 input. So this is essentially what we have here. Okay, so if you look at this, you see that this is 1, 2, 3, 4, 5 by 5. Okay, and there are 10 of this one. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9. Should be 10. Okay, and biases also. Do we have bias? I'm not sure. Okay, all right. I'll look that up. Okay. Yeah, we do have biases. Yes, these are the biases. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, I'm correct. Okay, so there are 10 of this, of the weights, and also 10 of the biases. All right, so I know I've said a lot. It might be a lot to take in for now, but I'm sure when you look at the notes, it will make better sense. Hopefully, I'm going to try to repeat the same thing again next week to let it sink in. Okay, so let's just continue and see how far we can go for the end of the day. All right, so if you look at the shape of this layer, like I said, of the convolved layer, you'd see that it is actually 10 by 3 by 5 by 5. There are 10 output channels, okay? All right, but we are convolving a 3 output image, so it's 10 by 3, and then the shape of that channel. So this is the output channel, the in channel, the channel size. Okay, and the bias, because there are 10 of these, the bias also will be 10. All right, so that's that. Okay, the max pool, like I said, takes the maximum of the kernel convolved at a spatial location. So let's see what that means. Okay, so we have the text input shape, we space it out, and then we make a kernel of size 2 by 2. Okay, all right. We pass it through a convolution, then we pass the result through the max pool. You would see that the values in a typical max pool, okay, just take the value within a spatial location. Okay, and it does not change. Well, it does change the shape based on the kernel size. So you have the input shape, which is 3 by 64 by 64. Okay. This is the unsqueezed dimension, which is 1 by, so this is 1, this is the batch size. Okay. Okay, can I see the screen? Okay. This is the batch size, this is the channel size, and this is the dimension of the image. Okay. If you pass this through a convolution layer with 10 output channel, okay, you can see that the shape of the image decreases. Okay, that's because we are passing it through, there's a calculation for determining the output size of the image eventually. It's not in this note, but maybe for this level, we really need it. Okay, so we have one, which is one same batch, but there are now 10 channels. Okay, by 62 by 62. Okay, if you now pass that through a max pool layer, okay, you get 1 by 10, but max pool squashes this because you're saying for each spatial location, you take the maximum. That reduces to 31 by 31. So this is actually dependent, the shape of this is dependent on the size of the kernel in the max pool. Okay. So this is another example. We have a random tensor. This is 1 by 1 by 2 by 2. So you can think of this as a grayscale image. Okay. we make a max pool layer. We pass it through a max pool layer. All right. So this will take the maximum at each kernel location. Okay. So this is a random tensor, this guy here. Okay. It is of shape 1 by 1 by 2 by 2. Now, if you now pass it through a 2 by 2 kernel, which is essentially just going to take the maximum of this. If you look closely, you see that the maximum of this is actually this number. So after the max pool, what we get is that number, which is the maximum. So this is the maximum value of the random tensor. So at the end, you only have just one because, well, you did not, there's no further stride apart from the first output. Oh yes, you're going to choose the kernel size during convolution. So most people use kernel size of 3. And then, yeah. So if you have a very large image, you might want to increase the kernel size, because once you do that, then you reduce the resolution of the image after each convolution. So these are all things that you get better intuition for once you train more networks. So the lecture notes are in the Telegram page. You can always download it from there. Okay. So to put it all together, we have the MNIST dataset. Okay. All right. Okay. It is of inputs 64 by 64 by 1. Okay. All right. Meaning it is 64 for a very large resolution image. So the number of images by 64 by 64 by 1. Okay. Is that in this shape or in this shape? But in PyTorch, you want to have them in this shape, where you have the number of images, okay, the number of channels, and the dimension of the image. Okay. I think for our example, we're using a 32 by 32 image. Okay. You want to pass that through a convolutional layer so that you can get 10 output channel. Okay. So at the end, depending on the kernel size, you get some number, but there are 10 output channel. Okay. If you pass it through a ReLU is not it's just a simple function. Okay. So it does a one-to-one mapping of the input pixel. So there's no learnable parameter here. So the shape remains the same. Okay. You pass it through another convolution, giving you 60 by 60 by 10. Okay. Pass it through a ReLU, it doesn't change the shape. But if you pass it through a max pool, it will reduce the spatial resolution. Okay. Now you can put it through your feed-forward neural network and get your prediction. So that's what we're going to do now. Okay. We set up the loss. I missed. Okay. Model 2 is not defined. I think I'm supposed to define my model 2 somewhere. I skipped some cell. This one. Okay. So we define some loss. Where am I missing out? Okay, I think I'm missing out a particular cell. Yeah, this is it. Okay. All right, so that's my model 2, which contains the convolutional layer. I defined loss, okay, and I can now train. Training for 3 epochs, and let's see how we do. So, by the way, because because we're using convolutions, max pool, we're obviously going to need more time to train. Okay, we're only training for 3 epochs. I think that shouldn't take too long. Okay, so I guess our exam is taking more than I expected. Okay. So the next cell compares the results, and if everything goes well, it will actually be 87%, which is better than our first model. Okay. So these are the output. The first one was 83, which was a linear layer. Okay. The second one is 75 when we added some nonlinear activation. Now we are back to 87. Okay. Mhm. So we can also compare the speeds of the model training, and also lastly, we look at the actual prediction and how good it is, and then we look at something called the confusion matrix. Okay. So let's see if it has started training already. So it has. So this is the first epoch. At the first epoch, we are getting a test accuracy of 75. Let's see what we have in the second epoch. Okay, so we have 87 at the second epoch, and possibly if you train it a lot longer for a longer time, we might get a much better um, result. So let's look at what we have in the second epoch. Third epoch. Okay, so this is the last epoch. We're only training for three. See. Alright, so let's see if it's coming out. Okay, I mean, it's even better than the result that we're seeing. So we're getting 88%. Okay, this is obviously better than.
Hello, sir. You have less than 3 minutes.
Okay,
Please, Karan.
all right. So this is obviously better than the first two model. Let's evaluate on all. Okay, all right. So we have 88%. The loss is much better. Okay, you can compare all three models here. Just put them in a data frame. So the first one give a loss of 0.47. The second one gave a higher loss, lower accuracy, and the third one gave the best loss with 80% accuracy. Okay, so these are the results. Um, this is the accuracy plotted as a bar chart, and you can simply make simple predictions. Okay, using that model. Okay, all right, and let's see how it does visually. Okay, so here it predicts that this is a sandal. It's true. Here it predicts this is a trouser. It predicts this is a sneaker. Okay, this is t-shirt. This is a dress. This is coat, sneaker, trouser. So it's actually doing very well. Okay, we can look at prediction over the whole test data sets. Um, okay, I don't have to touch the matrix, so I'll have to install this maybe in the next, before the next class. So the last thing you want to do is to look at the confusion matrix, which tells you how well your model is doing against the predicted class. Okay, so this is the true label, this is the predicted label. Okay, from this you can read off certain things like precision and the recall. So I think I'll stop here. When next we see, I'll probably have to go through this material one more time to get, for you all to get a better understanding. So the note is on Telegram. You can look it up, and if you have any questions, um, I think at the right time you can just send a message via Telegram. So thank you very much, and have a lovely day.